Hello,
thanks a lot. Indeed, you can call me Diego. Can you hear me? I guess yes.
Yes, yes.
Yes. And my last name is Altamirano. I think you got it right the first time, not the second one. Don't worry. So it's just Diego. It's okay. So let me share my screen. And you will confirm that you are able to see it.
Yes.
Great, thanks. So I kind of tried to challenge myself today to give a different type of the standard talks that sometimes we academics in general give in this kind of events. And what I wanted to give you is a bit of a flavor of the techniques that we use. And how is it that we can study objects that are really far. So that's why today I'm going to talk about how we study neutron stars, the techniques. So what you see in this first image on the top is the representation of how we would love to see a neutron star with the magnetic fields that are these loops that you see going out from the center ball in that image, and how that interacts with what we call an accretion disk, that is the kind of disc yellowish thing that you see on the sides. So I'll come back to that. Like any good book, there are parts, there are chapters, and my talk is something like that. And there's going to be 5 parts that might look or feel that they are disconnected, and you might think, why is this person talking about opera singers, or about motors, or about echoes, etc., etc. Stay with me, and you will see that hopefully, if it's a good book, all the things come together at the end and will all together give you an idea of what we are doing to try to understand these objects, neutron stars in particular. So the first part is put the things into context. Neutron stars can be completely isolated in space, so they are not interacting at all with the environment, or they can be interacting a bit with gas that is around, or if we are lucky, and this is the area of my research, they are interacting with another star. And how that looks is something like this. Let's see if it works. Yeah, so what we have is a neutron star that now you cannot see, and you have a star that it could be something like the sun. And when the two things are close together, close enough, the gravitational pull of the neutron star starts stealing or eating gas from the star. And that gas cannot fall directly to the neutron star. It has to actually lose what we call angular momentum, and it forms that accretion disk that I was showing you in the first image. So what I'm going to explain today is how we study neutron stars that are interacting with the gas that is falling on the neutron star itself. Why I am very specific is because, of course, when the neutron star is isolated, you have to study it in a different way, and you can actually do it. There is also a caveat. So these objects are very difficult to study, and there are a lot of techniques. Here I'm going to focus on 2 of them that are hopefully visual enough that you can understand what is happening. So the part 1, the first chapter, was a very short one, just to put you in context. Now let's go into something that you hopefully will recognize. And the part 2 in our journey is going to be about echoes, variability. When I talk about variabilities, things that change in time. So this can be, for example, lamp. If you have a lamp that is broken, or it's flashing and coming back, turning on and off, that's what we call variability. And I will start with sound, and I will talk about things that we know, but it's sound and it's not light. But the effect is exactly the same. And when later on we will remind ourselves that we cannot hear sound in space. Sound doesn't go in space, but we can see light, of course. So the idea of echoes, most of you, all of you, I'm sure, that have played with echoes before. The idea is that you are on one side and you have a wall, for example, on the other side, and you shout. The sound moves at a fixed speed, hits the wall, bounces back, and comes back to you. This is really nice because the speed of sound is fixed. Well, fixed in depending on the medium, but fixed if you are in the air, it is fixed. So if I send the sound, if I shout, and I check how long it takes for that sound to go to the wall and come back, then I can calculate very easily the distance to that wall. This is cool. I mean, to the wall, I could just walk there and measure it. But you could think of a more difficult problem, that is when you want to measure a distance to a mountain or to a hill that is far away. So if you have been lucky enough that you could be on a very nice natural place with hills far away, and you play this idea of the echo, it's a really cool thing. You shout, you wait, and then you hear your voice back. And sometimes you hear your voice again and again and again, every time with a lower volume until it disappears. So this is actually a type of technique that is being used in a lot of areas of research and actually innovation. So, for example, submarines use echoes to try to see what is below the water. Bats use echoes to know where they are going and try to hunt for food. We use echoes, or certain type of echoes, to actually study neutron stars. Of course, in an ideal case, what you would like to have is a machine that produces one particular sound that you can really recognize, send it to the hill in this case, and then that the sound comes back. So if you cannot see because the color is bad, but I'll change it. Give me a second. Where is it? So what we would like is that the sound goes and comes back and goes to the other hill and comes back, and then you start getting an idea of the structure of the hills and how far away they are. Now, in reality, when you go to the mountain, you don't have a perfect instrument. You are a person, and if you are lucky enough and you have a friend or a family member that is a singer and has a good voice, you know, then that's it, and you can actually see how the sound comes and goes. On a difficult situation is when you are together with one singer and another person, and everyone starts shouting at the same time, and then you get a lot of sounds going and coming to the mountain. So you are going to have Agatha Christie, sorry, never mind. The name is gone, never mind. So this person singing and the sound comes back, this other person singing and is coming back. And if you have your instrument somewhere here, you will receive the echoes of those sounds, and you can try to measure the shape of those hills. Now, it is more complicated than when you have one perfect instrument that sends one type of sound. Here we're talking about, in this ideal case, or sorry, in this case, just two persons singing. Now, those two persons that sing, they don't always sing at exactly the same pitch, the same tone. They use different voices. They change. They change the way they sing, and you have to take that into consideration. So now we're going to hear just 30 seconds of a part of an opera. Please hear this carefully, because then I will show you how we can identify what's going on just by analyzing the information there. So here we go. So a lot of things were happening there. We had the main singer, we had other people that were singing. There were extra noises that were being produced either by the public or even by the chatting between musicians. So imagine that that is happening in that mountain that you had. Can you actually do something about it? So one of the techniques that we use is something that is called spectroscopy. No, we create a spectrogram that is to try to analyze the different frequencies of the voices and the noise that is produced, in this case, in that video. So what you see here, what I'm going to show you and plot is something that is an evolution in time of that same piece. And what you see on the y-axis of this diagram is the different frequencies of the different sounds that you could hear. Yeah, I'm sure that if you close your eyes, you can hear some of the instruments and you can hear the main singer. But can you hear something else? Well, you will see that this first part, that you cannot really see it with my red marker, it's well in the first part is when the main singer is singing, and at a certain point she kind of runs out of energy, and someone goes and wind her in this case, and this is the 4 times that she gets winded, and then she starts singing again. Let's go and try to see this actually as it happens. With the mouse or with the hand that you see there, I will show you the evolution because you cannot see the line of. So it's synchronized between the voice and the plot. And suddenly the sound almost disappears. She runs out of energy. So the interesting thing is, here there is no image. I cannot see who is singing, how many other people were there, which instruments were there. But by studying this kind of diagram that we can produce, then you can already tell a lot about what is happening. Your brain actually does that. When you close your eyes and listen to this again, you kind of identify what's going on. Well, as astronomers, or when you want to study something in more detail, you cannot just do it in your brain. You have to actually do it, in this case, in a computer, so you can extract numbers and do something about them. So this is, again, what we're creating is a spectrogram. By the way, this is something that you can do at home, and I would really suggest you to do it if you want to have fun. You can do it with your own voice, and it's kind of a nice game to play with kids or with family members. I will let you know later or write me an email. The software is free to download, and actually you can do this. I did this morning. I was playing with this during the morning. But anyway, so coming back. So what if now the problem is more complicated? I wanted to have just one instrument with a single well-defined sound. Then actually 2 family members came and then made the things more complicated. Now I have a full 150 people coming to me, and they are all singing at the same time with different voices. And those voices go directly to my instrument, but also bounce in the hill and they go to my instrument. So now I have a lot of noise, a lot of sounds that are being measured in my instrument at the same time. And I need to try to understand what is happening with the structure of that hill. What is that hill about? If that was it would be good, but things are even more complicated, because you can also put a lot of sources of what we call noise. So in this case, I'm just putting an engine where maybe you would say the noise produced by the main engine is well defined, but actually all these parts are making a lot of noise, like the engines of your cars, and you have to actually try to differentiate what is what. So now imagine that you have the singers and the motors, all at the same time. So that is the real challenge, and it can be a potential challenge in actually on Earth trying to do that, because you cannot measure just by hand and go and measure it. So just to put it in context, imagine that instead of just having 1 or 2 very nice hills, you have something like this that is beautiful, and you want to get the structure of all these mountains. So you want to see where is higher, where is lower, what is the shape of those stones that you see there. So as I said, you start first maybe with very well-defined sounds that goes here and then comes back, but also goes direct. And because you have that information, then you can do it. And actually you can do it pretty precisely. The problem is that then, of course, you have another person that sings, that sound also hits the same place, comes to you and goes directly. And this is going everywhere. So I would have to scratch the whole thing to show you how many sounds you would be getting at the same time. Let's make it more complicated. You have your full 150 family members in here, plus the engines that you don't know exactly what they are, but they are there. And now let's make it even more complicated. Imagine that all these things are moving at the same time. So they are just moving and moving and moving, and you don't know exactly how they are moving, but they are moving. And you are already measuring, or the only thing that you are measuring is all the sounds that are coming back and recorded by your instrument. So sounds complicated. I hope that you see how complicated it is. Well, this is, as you will see in a minute, this is more or less what we have to deal with when we study binary systems that have a neutron star and actually a black hole as well. So this chapter finishes. I just wanted to give you an idea of how a simple problem can become very, very complex depending on the parameters that you have. And the thing that I want you to remember is basically that you can actually solve these problems. And the main reason why you can solve it is because you know that sound travels at a fixed speed. And you know that sound will go in one direction and bounce back, hit the wall, in this case of the rock, bounce in many directions, but one of those directions is where you are. And that is actually one of the things that we use a lot in astronomy. So, okay, that's part 2. So far, so good. That was sound, echoes. things changing, the sound changing. Now let's talk about something that we call energy spectral distributions of energy spectra. Don't worry, it's not as complicated as the name suggests. You hopefully all know that light has different colors, and we are only able to see in this range, actually in this range that we call the visible light, but there is light at different energies there, and there is what we call the infrared, the microwave, the radio, and you have the UV, the X-rays, gamma rays, and so on. And basically, what you are measuring here is temperature. Depending on the temperature of an object is where it will irradiate, in which wavelengths it will irradiate. So let me give you an example. We are, of course, used to seeing visible light, but not, our eyes cannot see in infrared. But we have machines that can do that. And on the right, you see just a building, as you would see it with your eyes. And probably if it becomes night, unless the lights are on, you wouldn't see the building at all. But if you now change to infrared, and this is just cameras that you can actually buy, you would see a lot more, and then you will see something different. And the different colors that you see on the left are basically telling you how hot or how cold certain parts of that building are. So as you can imagine, the windows are hotter than the walls that you see there. We do that actually, so this is done in Earth, and actually there are a lot of applications in real life, from medicine to industry to technology, in a lot of areas, just to change in which wavelength you see, and then suddenly you see something else, and then you understand much more. For example, this type of infrared cameras are generally used to find where your heat is going away in your house. But in astronomy, of course, because this is an astronomy class, an astronomy talk, we use it a lot to look at different astronomical systems or sources. And an example here is the sun, seen in infrared, ultraviolet, radio, and X-rays. And you can see that we are seeing different things, the same scale, but completely different things. And this is the way that we can learn about the sun. If we were looking only about in one wavelength, in one little part, then we learn about it, but our knowledge will be completely limited. It's very important to observe as much as you can in all the wavelengths, because that will give you the complete picture of the system. And this is another example. This is the Crab Nebula. And again, I'm not going to go into details, but the idea is that if you see it in radio and you see it in visible light, you see something completely different, and particularly look at what happens when you see it in X-rays. You can even see the structure around the neutron star there. So it's really amazing. So all this just to say that when you look at an object, and in this case, it's just a motor, that motor will have different temperatures, that different parts of that motor will emit a different type of light, just because it's a different temperature. Different parts of the motor will be at a different temperature and therefore emit a different type of light or wavelength. And here, this is not actually the real spectrum of the motor. I was having really troubles to find a correct one, but you can assume that that is more or less the shape of that spectrum. So even if you cannot see the motor, but you can measure the spectrum, then you can start getting an idea of more or less the shape of that engine, that motor. You're not going to get the details, but you will know whether it's for example 1,000 degrees, or it's 500 degrees, or it's at 0 degrees. So you will get a good idea. So if I come back to the original problem of measuring or trying to make a map of how high the mountains are, what you will have is this engines, and you will have all the people singing. And not only that, you will have also the spectrum of each of those components. And because in this case, it's just an engine that I just put it on top. But when we're talking about astronomical objects, it's engines that are part of the system. Then it can give us information about that accretion disk and how gas falls on the neutron star. Of course, don't forget that these things are also moving and rotating, and the spectrum as well. Sorry, the spectrum can be changing depending on where they are. So, as a summary of this chapter, is that the sounds, you are trying to solve a problem, and you know that the sound is coming from each engine, the sound coming from each singer. Both of together will help you map more or less what is the shape of that mountains that you are having. The spectrum of the engine and the singers will give you an idea of who is actually producing those sounds. Is it a singer? Is the singer taller, shorter? Is the engine bigger, smaller? Is the engine very big or very hot or not? All those pieces of information are the ones that we use to try to understand who is emitting the sound, and therefore trying to understand better how we map the mountains. Don't forget, an important thing is that we also have to have the spectrum of the mountains, because the mountains are also emitting, and we have to take that into in consideration. And except the mountains, everything is moving. So we need to take that into consideration. Hope I didn't lose you. It's just all the complications. So now let's go to astronomy. This is again an image that Vivien showed before. This was done for a black hole, but actually to what we're interested right now, it doesn't matter if it's a black hole in the center or a neutron star. From out far away, you see the same thing. You see the companion star, that is a star. You have an accretion disk, and you have that the disk becomes hotter and hotter as you get closer to the center. And in the center, a very small thing will be either the neutron star or the black hole. How do we study this? Well, what we have, luckily, is that the temperature of this disk will change. So we will have different spectrums. And somehow we have different kind of engines there that produce in light that is changing continuously. So it's not sound in this case, because sound, again, even if it produces sound will not reach us, but light will. And as well, if we are lucky, we'll have some very well-defined sounds, again, in terms of light, that we can identify with a physical process in an accretion disk. And if you are lucky enough, then you have something that we call, in this case, would look like a lighthouse that produces some light that goes and comes and goes and comes. So apologies, I'm changing from sound to light, but it's important, and I will mention later again. Remember, the example or the analogy is with sound, but sound is not what we use in astronomy, because sound will never reach us. But it's the same idea, it's with light. You can use light to through it, emit it, it will hit a wall and come back to you, and you can measure the same thing, because the speed of light is something that we know very well. So in terms of spectrum, and just to give you an idea, we use a small part of the spectrum because it's very difficult to get observations in all the wavelengths. But if you were able to get all the telescopes, so many telescopes of different types, observing your system at the same time, then you will get something that looks like this. This is data, this is data, there is some data there. I cannot actually touch it because otherwise I finish my sharing somehow. And then The interesting thing that I want to show you there is that if you are, for example, looking at the jet that is being emitted away from the system, then you want to look in radio. While if you want to see look at the very inner parts, those ones that are almost on the neutron star, or it could be the black hole, then you actually have to see in the very high energy part, where the material is super hot, so hot that actually they can only emit at very high energy. Okay, so now let's try to put all these things together. Yeah. So we will go to part 4, a reality check. And the first one I have to say is I like to do the analogy, and I think it works, and hopefully it works for you to get it. But remember, we do not hear sound coming from space. We only see light. So we can do exactly as the echoes, sound echoes that I was talking about, but we use light echoes. And that is what allows us to actually map the geometry of these systems, sometimes at the meter level or even smaller, so maybe even tens of centimeters, with very, very high accuracy, because light travels at a fixed speed. So again, this is the picture. We use the spectra together with the timing. We see how the things change and vary. Sometimes we have some extra things that help us. The only problem, and here is the reality check. This image looks really nice. You can see it big, you can see the parts. But the reality is that it is small in comparison to how far, well, it's small when you take into account how far it is. So to give you an idea of the challenge that we astronomers have to deal with, put this system, which looks really big, into a t-shirt. So that's the size of the system. So now you compress it to the size of a t-shirt. And now you put it here, basically just a bit farther away than the moon, when the moon is farther away from Earth. So this is what we need to deal with, is trying to identify what is the disk, what is the jet, what is the neutron star, how gas falls onto the neutron star, when it is just a size of a t-shirt or a stamp on a t-shirt on the other side of the moon. That is the challenge that we have. If we're lucky, as I told you, we have something that it's a lighthouse, and that helps us a lot. And just to give you an idea, if you wanted to study the lighthouse on a typical scenario, you would have to think and remember that we are here. This is Earth. Now Neptune is pretty far. The best picture that we have from Neptune, as far as I'm concerned, I'm not an expert, is this one, made with a very large telescope. This is the best resolution that we can get. And basically what you will have to try is to study me with a flashlight doing like this, and trying to understand what am I doing and who am I and why I'm doing like this on the surface of that planet. So it's super challenging. It's very, very, very small. But that's okay, because these things are challenging and we can do it. So real life research takes us to the instruments that we use, the techniques and the real data. So we talked about the context and the complexity. Now let me briefly tell you about the instruments that we use, the techniques and the real data. Instruments. So in this case, I study X-rays. Most of my research is in the X-rays, and the X-rays thankfully don't enter the atmosphere, but for astronomy it's bad. So you need to use space telescopes. And here I give you 3 examples. This is called NuSTAR, this is called Chandra, and this is called XMM Newton. But the one that I'm using now, it's called NICER, and this is a space station, and it's this small box there. That small box is more or less the size of your washing machine, and a real movie of it is this one. This is actually the telescope moving. This is not an animation made with a computer. This is actually someone from the space station making a movie of the camera. And what you see in the back are the solar panels of that of the ISS that also gives energy to the camera. So again, this is called NICER, and if you Google NICER NASA, you can get a lot of details about it. So how do we study the signals that are coming from so far away and from very small part of the sky? Well, we use something that is called Fourier Transforms. And I'm not going to talk about the technique itself, because that would be probably a couple of hours of just chatting and discussing and trying to explain how this works. But let me tell you that the Fourier transforms, or what Fourier discovered is that you can actually go from time domain, from getting all these signals into something that is Fourier domain. And the Fourier domain is actually what I was showing you at the beginning when I was showing you the spectrogram of that singer in the opera. There are two ways to see it. One is what we call a static power spectra. And what you see here is the frequency of the signal. So where it is, and if you compare again with sound, it would be the frequency of that sound. And this is the strength. And what you see here is a very sharp peak. That's actually when you detect a pulsar, a lighthouse. And that happens because the lighthouse is so stable that it will create this very, very beautiful signal. That is only in a few cases. In reality, in most of the cases, you detect something that is complicated like this. Again, this is frequency. It's basically rotations per second. And this tells you about the strength of that signal. And you see a lot of peaks here. Yeah. These peaks tell you about the different processes that are happening very close to the neutron star, how that gas is falling onto the compact object. So in certain way, what you are seeing is well-defined voices again, if you want it, and sources like engines that produce a lot of broader peaks that you know that there is some kind of engine, but there is a lot of noise as well. So that what I'm showing you there is actually real data. So this is a power spectra of a neutron star published on a real paper. This is another example just to show you again that there is these parts that we call noise because they are not peaked. They are very broad, but they are very well defined peaks. And those peaks can change in frequency. So this is again what I was saying. If you have everything rotating, sometimes you have a very well-defined frequency or voice, again, analogy, and that voice is changing. Like we were hearing the singer changing her voice. Well, here is the same. And this is the type of, this power spectra, this type of plot is the one that tells us in certain way what is happening very close to the black hole, to the neutron star. And we also can measure the delay between the signals. So imagine that I send, again, the echoes, a measure of the echoes. So what you see here, for example, is telling you that at different frequencies, so different voices, if you want, actually there is different delays. One goes faster and the other one goes slower, telling you a bit about the structure of all this. Of course, it's complicated, but I wanted to give you like just a taste of the complexity, but how we do it. Remember that we saw a spectrogram of a singer? Well, we can do the spectrogram as well of a neutron star. And if you are lucky enough, you will see something that is as clean as this. Again, time, and this is frequency. And what you see here is the evolution of a signal that basically translates on about 850 rotations per second. So imagine rotating around a neutron star or even around the Earth, whatever, 150 times per second. We are able to see that. And that tells us how gas falls onto the neutron star and interacts with those magnetic fields. Now, all that is not enough. So we also need the energy spectra. Remember that we talked about that. Well, this is a real energy spectra of a system, but that's the average energy spectra of all the things that are happening simultaneously. And our problem or our challenge is how you separate the different components, because you have 1, 2, 3 engines, you have the Singer here, you have the lighthouse, and all those have a spectra that add together to form this shape. So how do you translate that shape into 6 different components or 10 different components? And here is where the work of observers with theories, it's a must, because you start saying, well, I think that you have 4 engines, 1, 3, and 4, plus a Singer, plus something else. And then you start building what is happening. So I hope, so these were the 5 parts. I have to say, of course, it's complicated. It's not easy, but it is what we have. This is the tools that we have to be able to study those sources that's so far away. And anyway, it is complicated, but that's why it's fun. And I'll finish here. Thank you.
Well, thank you very much for that. That's very interesting talk, Diego. We don't seem to have any questions. I think you've frightened everybody into silence a bit, but I'll start with a question of my own, if I may, and we'll see if anybody else thinks of questions. If you've got an amateur telescope, and I mean, in my case, I've got an 11-inch telescope, and I have a spectrograph, what could I expect to see of a neutron star or in a close binary pair?
So nothing, and this is because the sources, this system, binary systems, are very, very weak. So remember when I was saying that basically you can, it's the same as putting everything into a stamp on your t-shirt and then put that on the other side of the moon, or even farther away if you are very interested in the inner parts. So to be able to study these systems, and if you wanted to do spectroscopy, basically, except for rare occasions, you would need 2 meters or 4 meter telescopes to get something useful. These are very unfortunate, but it's what it is.
Okay, well, thank you. We've still got a minute if anybody else has a question. No, nobody seems to have asked anything, so I'll say thank you very much for your interesting talk. There are some comments in the chat to the effect that your analogies were very interesting and help people to understand it. So